I mean, I'm guessing that we'll probably have people trickling in since
Yeah.
this is the first one after lunch. So welcome back. We're going to get started anyways, even though we'll probably say have a number of people trickling in over time. I am very interested to hear Chris's talk because I've always been intrigued by data consistency in distributed systems. So I hope you will find this interesting as well. Without further ado.
Hi. Okay, cool. Yep, so my name's Christopher Meiklejohn. I'm a PhD student at the University Catholic de Leuven in Belgium. I actually just started my PhD. Prior to that, I worked at Basho Technologies on the distributed database REAC, and then after that, I spent some time in gaming, mobile gaming at Machine Zone. And so this is a joint work between my university here and this other symbol here is the HasLab in Portugal. And this is a lot of this is funded by the EU under a seventh framework program project called Sync Free, which is about reducing the need to coordinate in distributed systems. And so a lot of my work is going to be framed around my PhD thesis, which is on this distributed programming language, which I'm creating called Lasp. And we're going to kind of talk about the motivation for Lasp and then kind of get into an example application and kind of slowly build up to the application that I'll present at the end. And so I think that maybe I've successfully or not successfully convinced everybody coming to this talk to think that this talk is about the Internet of Things. It is about the Internet of Things, but kind of more generally, what we're going to talk about today is the notion of edge computation. And so what I mean by edge computation is that we want to push both the data that we compute with and the computations or the programs themselves to the logical extremes of the network. And so when I mean the logical extremes of the network, I could be talking about a point of presence at a data center. I could be talking about geo-replicated data centers. I could be talking about mobile devices, like if I happen to push computation down to like a mobile app. Or I could be talking about like large-scale sensor networks. And so kind of all of these things can kind of be fit under this broad idea of edge computation. And so we kind of know what I mean when I say data, because data is generated at devices by user interactions or users working with an application or something like that. But kind of what do I mean by the notion of computations or programs? And so what we're specifically referring to here with edge computation is that we're talking about arbitrary computation. So anything that you could kind of express in a language like Java if you ran the JVM on a mobile device or a sensor, which you probably don't want to do, and or if you're using a language like Go or Haskell or any of these things like this. And so kind of arbitrary computation. We want to think about the same types of programs that we'd write if we just threw everything in a centralized database like Postgres and kind of just read it and computed with that data. And kind of, if we didn't mention any of kind of the academic history in edge computation or large-scale sensor networks, sensor networks now we think of devices that, we might put in our home to monitor the temperature of our house or to monitor if we've left a door open or something like that. But sensor networks have a very long history that I think is particularly interesting. And some systems that I'd like to highlight here are a large amount of the work that came out of Cornell University in the 90s, specifically systems such as directed diffusion or digest diffusion. And you don't really have to know what these systems are to appreciate them, but they were designed for high resilience and the notion of kind of the ability to self-organize. And so if you follow me on Twitter or happen to know anything about me, I am super into like computer history. I'm a super nerd about kind of old computer systems, and I think we have a lot to learn from them. And I find this work particularly interesting because in the historical context, some of these systems were funded by DARPA in the 90s. And if you kind of compare those systems back in the day to what we're building today, the constraint that they were operating under was that they wanted to have a bunch of sensors and put them in back of a plane. And they wanted to fly a plane over like a hostile area that they couldn't get people into. It's like kind of like a war zone, right? And they wanted the ability to drop the sensors out of the back of a plane and kind of have them like hit the ground. Some would survive, some wouldn't survive. And then they wanted these sensors to self-organize and compute some kind of result. So that's pretty crazy when we put it in the context of the kind of systems that we're building today with frameworks like Amazon Lambda, Amazon IoT, or any of these things that say, well, we'll just aggregate this information back and send it to a centralized data center. So I think the historical context is just kind of interesting to kind of pay attention to and think about while we're building new systems. So I'm gonna talk about hospital refrigerators today. So these this entire use case I'm going to present today is motivated by a bunch of Basho folks who went off and started another company to actually build this. And so I find studying the use case that they're building really interesting and seeing how we can do things a different way. And so we're going to talk about a bunch of hospital refrigerators that have a sensor associated with them that is going to monitor the temperature. And so if you imagine we have some really important stuff in here, maybe blood samples, maybe organs, who knows? And what we want to do is throw an alert if the temperature gets too warm, because that would be really bad. Or if it got too warm because we're underheating or undercooling or overheating or something like that. And so if we talk about kind of the typical topology or kind of the IoT reference architecture that we might use to build this application, we can imagine that we start with a bunch of refrigerators. These are things, and we put them on the internet, obviously, because that's what we have to do. And we can imagine that maybe these refrigerators generate samples every second, and they send them back to a data store. And so we can consider, for the sake of argument here, that data store is Hadoop distributed file system or something like that. And so if it was 2007, we might build something that looks like this. And we might have batch jobs in Hadoop that would iterate over that data set. That data set would be growing. We'd do some iteration, time-bounded iteration, and we'd trigger some alert if we happen to find some sort of bad condition in the system. Now, it's 2016, so maybe what we would do is we'd use something like Spark instead, or maybe Spark Streaming, right? And so this is kind of the incremental improvement on top of Hadoop. And so really the structure stays the same, right? Instead of thinking about it as batch processing, what we do is we break up our stream into micro batches, and once we break up that stream into micro batches, we do processing, and then we send alerts. And so even if you were to build this architecture today with Amazon IoT, this architecture is focused on aggregation of information at a centralized point, like a data center, and then you perform your computation once you aggregate that data at the data center. And so if we simplify the diagram and talk about what an ideal execution of this infrastructure might look like, it would look something like this. So we have our refrigerators. We generate a sample here saying everything's fine, goes to a Hadoop file system, and nothing happens. Now, if we generate the sample that says that, oh my God, everything's really bad, and we send that over the internet to Hadoop distributed file system, then maybe the Spark system triggers some alert because it sees the bad sample, and then it triggers a phone call to be made to somebody to say, hey, you got to fix this. And so if we want to kind of just trivially start poking holes at this infrastructure, the first one is this. OK. And there it is. And so computers are hard. And yeah, so this, and so if we want to trivially start poking holes in this infrastructure, the first thing we can look at is what happens if we have a lack of connectivity. And so if we generate some event here, and we transmit it, and everything's fine, and then we have this kind of pathological case where the internet connection goes down, and we generate a bad sample, well, all we can really do is buffer these events until we come back online, if we rely on centralized reporting to trigger alerts. And so this is less than ideal, because we know that networks have problems all the time. And we know that systems get partitioned, and all sorts of things can happen. Somebody can trip over a switch in an office or something and disconnect it, or there could be wireless interference or something like that. And so kind of the first thing that we could do is we could say, well, what happens if we decide to take local decisions? So now if we can push some of the code that needs to do the alerting down to the device, well, now I can trigger the alert myself. I can make the call, like the sensor that's in the field can make the call. And so now we have a bit more recency if we think about how we can do alerting. We can alert faster, we can react to errors faster. And so what I like to highlight here is the notion of local decisions is not new. In the 80s, and I worked in telecom in the 90s, and this was very common to have ISDN lines or T1s that were backed by out-of-band POTS lines that would kind of send alerts to say the T1's down or something like this, or there was a connectivity problem. And so the notion of local decisions is not really new if we think about it that way. Now, if we kind of move a little bit forward in time, with the invention of systems like SANs and NASs, this isn't new either. And I was in telecom at the time, and we deployed some of EMC's early NAS equipment And EMC, you'd plug a phone line into the NAS, and if the box started taking CRCs on a disk, it would call EMC, and then the next day you'd have a knock on the door, and some EMC tech would be there with a brand new drive, and you didn't even know drive was having a problem. And so this is really nice. And so there's already been precedent set about kind of pushing local decisions to the devices so that they can continue operating. And just a little aside, we've also kind of we've briefly talked with companies like PG&E, which is a large utility provider in the San Francisco Bay Area. And in their case, they're like, well, we have to make local decisions because if a power grid gets overloaded, we can't use the power grid to send the alert. So we need an out-of-band mechanism for either transmitting data to kind of facilitate delivery of these alerts, or we need a mechanism for taking local decisions. And so that's really expensive because now I need what, like phone lines, I need hardware, I need things that can page people or call people. That's complicated. And so if we throw a little bit of internet power or wireless power at this, maybe there's another direction we could take. And so maybe we can think of the idea of transitive dissemination. And so in this case, I run into the same situation where the internet connection is down and I can't transmit the sample back to the data center. But maybe I have another way of communicating through Bluetooth or another kind of out-of-band, out of the Wi-Fi or internet path, where I can communicate with another device that's in a near-field range that does have connectivity. And then that device can deliver the event on my behalf. And kind of if we think about this, we can trivially poke holes at this because, to guarantee with very high probability through transitive delivery, that means that, in the case where we want to prevent against maximum network emissions on the network, we need to send it on every single possible path. And when we aggregate this back at the data center, we have to deal with the notion of deduplication, or knowing if we've seen an event that's already been delivered. And we have to deal with this because messages can, if we have this notion of transitive dissemination, and we know devices can go offline, we have no guarantees on when messages will be delivered, or if they'll be delivered in a predictable order. So these things can come in any arbitrary order. So if we kind of just wanted to picture what might be somewhat ideal, let's imagine just kind of a perfect world scenario if we could. Well, maybe we have a notion that rather than transmitting events from the devices, each device just has a state. It has a piece of mutable state, right? So rather than transmitting an unbounded, indefinite stream of events, we know that we don't have to care about the positive events, but we have to know that we're getting some events, and the network hasn't prevented them from delivering any events. And so maybe what we could do is rather ship a dictionary or some sort of object of mutable state that I can combine and put the status of all those refrigerators in. And so here we could just imagine, maybe we have a simple case here, we can imagine a dictionary where the keys are the refrigerator names and the values in the dictionary are the status of whether it's okay. And so for something like this to work, if we wanted to imagine kind of the ideal case, for this to work, we know that there are certain criteria that we need to have, some invariants that we have to preserve. And so one of these invariants is that if these things receive the updates, the changes to that shared state out of order, I need to know that when I deliver all of those events, that the order of delivery will not matter, and I can compare these things. And so we can think of this as if you have a dictionary, let's say, or let's imagine you have a set on a sequential set, and you perform add and remove operations, you know that add and remove don't necessarily commute. You can't reorder them and guarantee the same output unless you use a set that's designed for ensuring that order doesn't matter. And you could think of a case where I reorder a removal before an add, or vice versa, and the set and a different interleaving might come out with a different output. And so we need to ensure that we have a way to say that the order doesn't matter, because we know that ordering is extremely difficult to do in practice. And this is why we have systems like Zookeeper, because Zookeeper gives us order. And so maybe what we're looking at isn't having something like HDFS. And if anybody can do the alerting, then that means that any of these refrigerators, or the one that has a phone connected to it, can do the alerting for us, right? And so we have this trade-off that says, well, more of the devices that get the state, they can act on the other's behalf. And there's kind of this trade-off between, how many guarantees we're able to provide on the network and how soon we can alert on something. And this is kind of the trade-off that we want to think. And this is kind of a recency trade-off that you would make. If you coordinate more, you can get higher recency, but you know that you're less resilient to network problems. And so the kind of core ideas I'd like you to take away from this little kind of example application are two ideas here. Rather than imagining designing applications around consuming unbounded streams of events where you care about very few of those events, or maybe you care about outliers in that event stream, maybe you can model this with mutable state more efficiently. And we're going to show one approach to doing that. And the second idea the second kind of point I want to get across here is that local decisions are good because they allow us to have applications that are more resilient to network failures. And we know that this is we can't imagine a world where we have a perfect network. I mean, if you have a mobile phone and you go down into the subway, you're going to be offline at some point in time, and you're going to kind of work with an app. And some apps just won't let you do anything if you're offline. And so kind of pushing computation to the device gives us higher availability and gives us higher resilience. And so what we're really talking about here are trade-offs on consistency models. And so if I didn't talk about databases, I would kind of be hiding a lot of the prior work in this area. And so what we're going to do is we're going to talk about kind of the two major, kind of the dichotomy we think about. It's much more like a spectrum, but we're going to think of, of a very fine-grained spectrum, but we're going to think about it kind of as a dichotomy for simplicity. And so the first idea here is the notion of strong consistency, or something you'd get from a system like Paxos, or a Paxos with state machine replication, Zookeeper, or if you have a single database, something like Postgres without replication. And so in the database world, if I have one database and I have two clients, and I put an object on replica 1, the green circle, and I issue two concurrent read operations from client 1 and client 2, when client 1 goes to modify the object to turn it into this blue square, client 1 will issue what's kind of referred to in the literature as a compare and swap. And this operation is going to succeed if the operation observed is kind of swappable here, right? If the value hasn't changed from underneath client 1. And this gives us this nice kind of changes are based on visible things. It gives us this nice total order across all the events. And so this change will succeed because the observed value is still the current value at the data store. Now, client 2 already has a copy of that state. It's already got a copy from a read. And so if client 2 goes to perform a compare and swap and says the last observed value I saw was the circle, then what we want to do in a system like Zookeeper or Console or something like this is refuse that change, because it means that potentially the change that made me go from the green circle to the red triangle, the red diamond, is not necessarily valid anymore. I might have based my change on state that was no longer the right state. And so this is the way many of the database systems we have today work. Now, I talked about a single replica. I'm not going to diagram Paxos any more than this. But what you can imagine is if I had to guarantee consistency across a series of machines, and why do you replicate? You replicate so you're tolerant to faults. If I have to guarantee this, we can see that this takes a lot of effort. This takes a lot of code. It takes a lot of time, because we have to get people to agree. We have to get all of the replicas to agree at a point in time that they all have the right value, and they all confirm that, it's a valid value that somebody actually wrote, and everybody has that value, or a quorum, majority quorum, or something. And so this little cloud here is just like time. It takes very long for this to happen. And so this is really bad in the case of mobile devices, where you might want to have mobile devices work with state, but if they're offline, they can't coordinate. How do you get a majority across 1 million mobile instances of an application when 70% might be offline at a particular time because of where they're located? And so kind of in the 2000s, when high availability services came around, and sites like Amazon started getting big, and Google started getting very big, and started working with larger amounts of data, we kind of introduced this notion that goes back at least to 1983, is kind of one of the pinnacle papers on this work, of eventual consistency. And eventual consistency says, well, if I kind of explore the same scenario where I have the copy of the object replicated against 3 replicas, and I read the value, I'm going to talk to kind of a quorum here. And so again, I have my concurrent reads where client 1 and, I'll go back, client 1 and client 2 get that state. There's an error in that slide, missing the circle. And now if client 1 goes to write back the blue square, that will be replicated to those nodes. And it could be just across a majority. I'm showing a perfect execution here. Now when client 2 goes to write its change to the server, same scenario, they both read at the same time concurrently, and then performed operations concurrently. What the system is going to do in an eventually consistent system without like an arbitration order is it's going to store both values. So it's going to store both the blue square and the red diamond. And now it pushes the responsibility on the user that says, next time you read this object, there's 2 copies of it, they're divergent, we don't know the relationship between them, so it's up to you to figure out how to resolve that divergence and write it back. And so if we look at eventually consistent databases, for instance, the one that I worked on, React, this is React's default behavior in React 2.0. Amazon's Dynamo system also talks about this behavior quite a bit. If we look at a system like Cassandra, well, Cassandra doesn't need to store both values because Cassandra introduces arbitration, where it will pick the last one with the most recent physical timestamp provided by the user. And we can see this is problematic because that means that the write that came before me, if it happened afterwards in actual physical time, might just disappear. We might just lose that data. And so losing data is bad, and we don't want to do that. And so what we'd like to argue, or what I'm going to argue in this talk, is that we want to think about a system where rather than racing to a database to give your values to it and have that database say okay and keep that value as truth, I want to convince you that thinking about clients that are generating their own data are the source of truth for that own data, and that they should share that data when we want to compute with it, but they should be able to share that in a peer-to-peer manner or through a database or however. But we should kind of invert the model to think that clients have their own data. And so clients will get their own data, and they will share that data with each other, and hopefully, regardless of network ordering, if we build the system right, the order won't matter that we deliver these events in. The other notion I want to drive home here is the notion of provenance and mergeability. And so what I mean by this, and I'll do a quick diagram to show, is imagine that refrigerator A observes events A and C, and the second refrigerator observes events A and B. Now, if I have some function or some computer program that I've written and I've given to both refrigerators, I would like it where if I apply that same function with just some of the inputs, the output value I produce, D, has some notion. It tracks the inputs that caused it to get that aggregate to build it. So if F is building an aggregate, it knows the inputs it observed to build that aggregate. And this allows us to say that we know that D and D double prime here, D prime and D double prime, are related because they share this kind of one event. They share the same program, and they have one overlapping event, which is this green circle. And so the property that this gives us is that we are able to take the results of programs and combine them. So I can produce some program over here on partial outputs and some program over here on partial outputs and combine them. And so we can think of this as kind of a map phase, with the merge being the reduce phase. And the interesting things here are that in normal MapReduce, a lot of this is extremely difficult to do because overlapping events can be problematic unless you explicitly instrument that. And finally, this notion where I track the inputs is difficult to do. And so to kind of frame this in a more industry setting, to think about, this is a crazy idea, what does it mean? This is how Spark works. Similarly, it's very close, but at a much coarse-grained level. And so what Spark will do is that if Spark is handling multiple mappers and building some reduce phase from those multiple mappers, Spark will track where those inputs come from. So if a partition happens to go down, it will say, I know I'm missing the data from this partition. So we can think of Spark as being kind of this idea, not on a per data item level, but kind of on a per set of data or per node or per partition level. So this is not a crazy idea because we've seen it before. And there's a lot of fault injection stuff that uses this similarly to track how data moves through a network and how we know where a source that might have happened way over here can be traced to some error that happened way over here in systems like lineage-driven fault injection. Okay, and so these are kind of like the two ideas. And so what I'm going to do now is talk about the work that's already existed, that's being done by me and my research group and my colleagues, that are steps that allow us to move in this direction. And so I'm going to break this into three components. The first component I'm going to talk about is something referred to as CRDTs. And what these are data structures that are designed for distribution and convergence. And so it says that I can take a data structure, and I can replicate it, and I can play the events in any order, I can duplicate them, I can rebatch them, and I guarantee that all the replicas will arrive at the same result. So this is kind of a determinism guarantee. Since CRDTs are on a per-object basis, I'm going to talk about a system that we're building called lattice processing, or Lasp for short, which extends this property, this mergeable property, from a single data item to an actual program. And we can think of a program as a composition of kind of data structures and functions. And finally, I'm going to talk about how do we scale this to hundreds of nodes, thousands of nodes, tens of thousands of nodes. And so we do this with a runtime system that we've been working on called selective hearing. So to give a brief overview of CRDTs, so CRDTs are a collection of data types. They come in a variety of flavors here. Sets, counters, registers are like kind of like just like you can think of an integer or like a string as a register. We have things like flags, which are booleans that can only move in one direction. So it's a boolean that can move from false to true or true to false, but can't go back and forth. And finally, maps, or kind of dictionaries, which is a recursive data type. And what CRDTs do is they fulfill this property that's desirable in distributed systems called strong eventual consistency. And what strong eventual consistency says is that if I have a data item that I replicate, and I play the events in any order, so given some finite set of events, I play those events to the data structures. They don't have to, I don't have to play all of them to every data structure. I just have to play some of them to get it so that every data structure sees, each replica sees like at least one of the events. I can duplicate these events, I can rebatch these events, and I can reorder these events. Given that, as long as all of the replicas see every update, and this can be fulfilled through peer-to-peer transitive communication between all of the clients in your system, that I guarantee that the output, the final value seen by all of the clients will be the same. And so this is something that's difficult to do. And so a trivial way to fulfill this is to use physical timestamps. The problem is that you can have data loss with physical timestamps. And so I'm going to give an example here with a diagram. So we can imagine we have three replicas, A, B, and C. And what I want to model is a set where I can add and remove an element from the set multiple times. And so I'm going to model the set differently to achieve this goal. And so in the upper left-hand corner, we're going to have the operation that's invoked by the client, which is a add one. And in the bottom right-hand kind of oval, I'm going to represent the state that the data structure has. And so when I add one to the set, I'm going to model a data structure as a triple. It's going to have the element 1, which is what I've added. I'm going to generate a unique identifier representing that addition, which is going to be that lowercase a in that first set. And then the second set I'm going to leave empty. And so the way to read this is that 1 has been added at logical, this one replica has observed 1 added at logical time a, and it observed no removals at any logical time. And so then it replicates those results out to the other replicas. Now, if concurrently replica C also adds 1, this is a different operation. And so replica C will generate a unique constant, represented here by lowercase c, and it will add that into the add set, saying that I have observed 1 added at logical time c and not removed. Now, if C goes to remove 1 from the set before the replication has happened, then C will take the additions and union them into the removals. And so we see here that replica C only observed the addition at logical time C, so it can only remove it at logical time C. So now when I deliver all the messages, I see that all of the replicas end up with the same result. 1 is in the set, it was added at logical time A and at logical time C, but it was also removed at logical time C. So the 1 addition at logical time A wins, and the value is still in the set. And so this is nice because I can reorder all of these messages, and I can kind of delay things and partition clients offline, and I can guarantee that I can get the same result. I don't need to synchronize, I don't need to take out a mutex or a semaphore or use a monitor. I don't have to use any of the kind of standard locking mechanisms for enforcing order because the data structure can handle kind of the non-determinism in scheduling. So this is really nice, but the only property that this gives us is that on a per data structure basis, I get this guarantee. So if I have a regular programming language like Java, or imperative programming language like Java, and I read the value of this set, and I perform an action based on the actual value 1, that action that I base that on won't necessarily be executed at the same time as all the replicas. And that is because I'm looking at the kind of external value, and I'm not working with this internal representation that allows me to be tolerant to reordering. And so to solve this problem of composition, we are working on a system called Lasp, which is a kind of subset of functional programming for sets currently, that extends this convergence property to a program that's composed of a bunch of these data structures. And so the way to think about this, the way this system works, is that in terms of how in a language like Lisp, where the core data abstraction, you kind of express everything in terms of the list. In our language, we kind of formalize everything in terms of lattices. And so that data structure I showed you before forms a bounded join semi-lattice, and this is kind of the property, and then we have a bunch of lattice homomorphisms. And so there's a very nice principled kind of mathematical foundation behind this that allows us to kind of formally prove certain properties about how these things will converge correctly. And so the language, this is kind of a pseudocode representation of what the language kind of looks like right now. It's just an embedded DSL in Erlang. And so here we can just imagine, and so there's explicit type specifications here because Erlang no types. And so here we can imagine that we have a set called S1. We have another set called S2. We're going to add some elements to S1. And then what I want to do is apply like a map function to kind of take the elements from S1 and map them into S2. And so since S1 is a piece of mutable state that can change over time, every time S1 changes, I'm also going to change S2. And so this allows me to build this nice dataflow graph. And so we have functions for like doing like a fold, doing like a map, a filter, Cartesian product, and union and intersection and stuff. So like kind of your standard operations that are across collection types, specifically sets, because guaranteeing some of these properties with ordered data structures is much more difficult. And so you think, for the map function, this is pretty trivial to do. I just kind of take that internal representation with all those unique identifiers and kind of map it through. And so for map, it's pretty trivial. For some of the others, it's not. And this kind of boils to a general way of thinking about the causality of a particular object over time. Now, you might be saying, this sounds really expensive to send on the wire. There's these data structures. They track all the operations. How do you do this, right? This is really inefficient if I have to store every single update. And so the starting point is to work around this concept that's being worked on by our colleagues in Portugal, which is this notion of delta state. And so the idea here says, well, if I only change a part of that really big data structure, I should only have to send the part that changed. And so there's a nice formalism that allows us to express this in a very nice way that relates strongly to semi-lattices. And the general intuition here is that you operate on a local data structure that you have on your mobile device, for instance, and then you queue up updates for the other clients, and then when you have connectivity with those other clients, you ship these deltas. And you have to be very principled with the way you handle these, because they have to be ordered in a particular way, which is easy to fulfill if you're doing ordering between 2 people rather than across 10,000 people. And so this is great, but if a client goes offline and never comes back, that means that I have to store their updates forever. And so what we do is we fall back to sending full data structures in the event that a client is partitioned too long or isn't connected for a very long time. And so to give you kind of a graphical intuition of how this works, if we imagine we have 4 refrigerators, and I generate some update at the first refrigerator, the big green circle, what I'm going to do is kind of buffer the updates to the other 3 refrigerators here as a small circle representation of just the change that caused us to have that change. Similarly, another client may do the same and buffer those changes. And now if the first refrigerator generates this red kind of change, we store this buffer, and these items in the buffer have to be ordered to guarantee convergence properly. When we go to synchronize these 2 refrigerators, if they're operating on the same state, what we do is we first we take the queued updates on the buffer and ship them to the other data structure. We perform that operation in reverse, so we ship the buffer back from the other client, and then the objects are converged to the same state. Again, the core properties here that allow us to do this is that we can ship these we can have concurrent updates, we always have a way to merge things, and we always have a way to kind of do this peer-to-peer dissemination and not have to worry about ordering. So we're trying to reduce the amount of synchronization in the system. Okay, and so to kind of talk about the final piece, which is this idea of how do we distribute this efficiently. So again, a lot of this is work in progress. What we use is a runtime system that we've been prototyping called selective hearing. And so if you're familiar with distributed systems literature, there's a notion of protocols called gossip protocols or epidemic protocols. And the way these protocols work is that they guarantee extremely high probability on message delivery to achieve atomic broadcast. But the way they do this is they do peer-to-peer kind of dissemination. So I send to some of my peers, they send to some of their peers, and kind of it disseminates kind of like a disease or an epidemic, right? And so we built a runtime system for distributing program scope this way. And the challenge in making this work is that if you can't make any ordering guarantees on the network, you need to build from a language that doesn't have ordering, right? So you couldn't have another system that's backed by an epidemic broadcast protocol if it requires locking and totally ordering messages. Or you could, but it would be very, very slow, because you'd have to kind of get agreement on who held a lock before you could apply some update, and then kind of release that lock in a safe manner. And so the only way that we can kind of pair these protocols together well is that we have to have something that's tolerant to reordering. And the reason that we target epidemic broadcast protocols is it's been shown that these are great protocols for message delivery and state dissemination, where you want extremely high probability of delivery with very high churn and fault rates. And so systems like this can achieve, over clusters of 10 to 20,000 of nodes, can achieve upwards at 99% delivery at 90% churn and failure for some of these protocols. So these are highly resilient, which is nice when you're trying to build a system that operates over many mobile devices. And so to give you an intuition of kind of how we think about programming these is the way these protocols work is we start with a membership overlay. And so we build an overlay network of all of the kind of the parties that are involved in the computation. And we can think of this as a kind of a directed graph. But this is still rather inefficient at at a very high number of nodes for something like 10 to 20,000 nodes. And it can even start to see problems at 5,000 nodes. And so what we have to do is we build a broadcast overlay on top of this, which kind of builds a tree within the overlay for doing optimistic dissemination. So if clients are online, we can distribute data to them extremely quickly through this broadcast tree. But we have to have a fallback mechanism for clients that get partitioned. And so roughly the overlay is going to look something like this, where we have kind of the tree that we've established through the network of clients. Each client maintains their own tree, so each tree is rooted at each client. They have a broadcast tree. And then this dotted line kind of represents a path that's not used, but it's used for repair under a network partition. So if we happen to lose one of the links, we'll use that path to repair the tree. And so the protocol has a mechanism for knowing when messages have been delivered and kind of repairing those trees. Each node in this graph could either be something like a mobile phone, or it could be something like a distributed hash table. And so this gives us the flexibility to kind of build an overlay over systems that are highly resilient, that might be storing like security information like keys, or might be storing some state that needs to be persisted, but also gives us the same way of looking at mobile devices, where we don't care if a mobile device potentially goes offline forever, because people are going to run into situations where they might drop their phone on the street and just buy a new one, right? And so that would be a client that potentially went away and never came back. And so we kind of want a unified model of thinking about how these clients communicate with each other and separate out the persistence concern to kind of, the abstraction that sits a layer below the overlay network. And finally, where does our stuff fit in? Well, our stuff fits in kind of at this little turquoise, I guess, color here, which is kind of our programming language execution, where we kind of apply operations to state, and then we kind of disseminate it through this graph to the different types of clients that we have. Okay. And so to kind of just wrap up, to walk through an example application and then do a wrap up, we're going to talk about kind of the major application that we've been developing as part of an agreement with our research project and Rovio Entertainment, who obviously makes Angry Birds. And so in this example, what we have is an advertisement counter that's deployed on mobile devices. And so you can imagine you have a game that's going to display ads, and you want to track the number of impressions. So there's a bunch of ads that get displayed on devices. They periodically synchronize. These clients are going to go offline. They're going to be periodically connected. We want to continue displaying ads while they're offline. We want to store all of the impressions for each of the ads. And then we want to disable advertisements once they reach a minimum number of impressions. So under contractual obligation, they say that an ad has to be displayed a particular number of times as like a lower bound on the display. And so if we kind of imagine what the data flow graph for this application might look like, it looks something like this, and we'll zoom in to get more detail. And so we can use the primitives in our language to kind of group, we have counters that represent the number of times ads have been displayed. We can kind of group them together, so maybe we take all our ads and we union them together. Maybe we say we only want to display ads that have valid contracts, and so we can kind of just compute so this is a data flow representation here of a SQL join, so we're just kind of computing the product of ads and contracts and then taking it where we have a match. So kind of this is the equivalent to an inner join here that would just produce just a list of ads that have valid contracts. And so what we want to do is we want to have our clients periodically synchronize with the server. And when they periodically synchronize with the server, they get a copy of these advertisement counters. Those clients will increment those advertisement counters as they display ads, and then periodically they'll ship their state, like through that delta mechanism I just showed you, back to the server, where that state will be incorporated. So we can think of the server as having kind of a view that's like monotonically increasing, but lagging behind from the global view, because some clients will have incremented it, but have not synchronized yet. And then eventually we'll just kind of threshold on the value of the advertisement and disable it. And so we have a way, as I showed earlier, where we can remove things from sets or remove things from the language, but model that in a way where it looks like the state is always growing. And that's kind of how we track the additions and removals. And so the kind of interesting idea here is that the advertisement counter is completely modeled through state growth in an efficient way of tracking state growth. And so we don't have to deal with the fact that in distributed systems, it's very hard without coordination to retract some piece of knowledge, because you have to get agreement from everybody about the retraction, because you can't tell the difference between the retraction and the non-observance of the event unless you model it in a way that always accumulates information. What's nice about this design is that it's arbitrarily it can be arbitrarily distributed. So any of these data structures or computations can live on any other node. We're tolerant to reordering. We're tolerant to network anomalies. And finally, the notion of divergence says that if for some reason I don't synchronize immediately, I know that I'm going to be lagging behind the counter a bit. And so if we think of, well, if I increment the counter and immediately synchronize with the server, well, I guarantee that I won't overcount, because I'm going to kind of perform this atomic, like I'm going to increment the counter and show the ad. But if I want to operate offline, I can make that synchronization interval be every 10 messages, or every minute, or every hour, right? And so we can think that there's a trade-off between how far we overcount versus, if we want to enforce a bound. And so kind of the important piece to take away here is that all of this still works the same way that I've shown before. Even though the server does some additional computation than the rest of the clients do, all of the devices still synchronize with each other over this overlay in a peer-to-peer fashion. It's always peer-to-peer synchronization. I don't have to draw a distinction between the API that my server uses versus my peer-to-peer API. Everything is one protocol, and that protocol powers everything. And so what's special about a server in this model? Well, the server has to be special for a couple reasons, right? Servers are essentially peers that can do all the same things that clients can, or clients can do all the same things that servers can. But servers kind of are in a special role where they have to be trusted to perform some sort of kind of exactly once operation. And so in the advertisement counter I just gave you, example I just gave you, if we were about to bill the company because they displayed 50,000 ads, we don't have a way to model charging a credit card in a semi-lattice where it guarantees I can reorder it and rebatch it and then replay the event multiple times without doing all of the work of having unique identifiers and all this stuff, right? So there is some synchronization inherent here, because at least some part of the operation, even if I use sequence numbers, has to be synchronized to get agreement on the sequence number. And so the idea here is that rather than think about operations that I can do in parallel, why don't we start from building a system where I assume that I can do everything in parallel and then kind of point out the particular parts where I need synchronization to be performed. And so what you want to do is have a system that kind of allows you to build these systems that are parallel and concurrent that are safe by construction, rather than have it where you have to reason about where to put locks, because sometimes we don't get that right, and we know that live locks and deadlocks are difficult things to debug in practice. Okay, and so I guess the general idea that I want to drive home, general idea I'd like to drive home with the talk here is that what we've done is we've kind of presented a model where we're building up from zero synchronization. We're not building a model where we're trying to reduce synchronization in a system. We're not trying to get extra performance out of the system, because we start from building where we have a base where we can get these gains from concurrency and parallelism and have a system that's very resilient to failures that can perform well. And so I want to kind of say how can I relate this in terms that are much less academic? Well, the way I think about it is rather than taking Zookeeper and building a system around Zookeeper, what we want to do is build a bunch of systems that can kind of work in concert together that are safe. So we have to have a language where distribution and reordering is safe by construction. But we just use Zookeeper where we need to coordinate, where we need to synchronize to guarantee something. And some problems are a problem of synchronization, like atomic visibility, or even problems of like kind of getting agreement to do something like garbage collection or something like that. And so kind of if I wanted to quickly highlight what I think are the challenges moving forward, the first one is the problem of state explosion, which is probably pretty clear to see from the presentation. And so if I had a set and a counter, and I wanted to use a fold operation to count the cardinality of the set, I would have this, and I would transform my set into my counter, and then I would do that again, and then I'd do that again. And what we can see here is that for a set that's only got one element that's been removed a bunch of times, the space complexity for my counter is actually much larger than my space complexity for the fold itself, for the source of the fold, the set itself. And so maybe in this case, it's more efficient to find a way to disseminate the source and move the computation to compute cardinality versus the opposite. And so finding clever ways of expressing this state, and this is this provenance, this lineage data here, all of that data is what's needed to ensure this mergeability and this combinability. Finally, the second point here is that security is a difficult thing we have to think about, and we have some preliminary work on information flow control to kind of solve this. But if I have this idea of transitive dissemination, it doesn't mean that just because there's a path between me and somebody I want to send a message to, it doesn't mean that I actually want to send that data on that path, because that might be a path that I shouldn't send data. Maybe I shouldn't send credit card data through one of my clients, right? And so we have to think about how we build these systems where we can derive correct flows of information if we want to kind of build peer-to-peer networks. And so, you could think that maybe Bitcoin or something like that, or related to the blockchain, is maybe a potential solution for something like that. Or maybe there are other approaches, And so IFC actually can get a good amount of the way there for doing it under networks that are non-adversarial. And finally, the problem of expressiveness, obviously, the more kind of theoretical PL side of this says, well, I have these nice data structures that give me all these properties of merging and combining and all of this great stuff, and I don't have to worry about ordering or sequencing. But all of these things rely on this kind of lattice theory that we're building on top of, which is great for distributed systems because they're very analogous. The problem here is that lattices, by definition, joint semi-lattices, by definition, require that all of the events in your system be associative, commutative, and idempotent. So again, that rebatching property, that reordering property, and the ability to replay things. And so the question is kind of if we were to extract out a core calculus and see what this language really means from a mathematical point of view, are there types of programs that we can't express? Well, probably, right? Because things like division, I mean, that's a trivial case, right, that we can't model in this way. And so we kind of have to figure out what the bounds are and figure out what kind of applications that we can build using this system. We have a bunch of, there's a bunch of papers and stuff if you're into reading about things rather than listening to them. But again, to kind of summarize in 2 slides here, what I'd like to say is that what I've shown you today are 3 independently successful techniques. CRDTs, the data structures that we use, have been successfully deployed by the London National Health Service for all of their kind of metadata around describing prescriptions and customer records, and they've had tremendous success. They moved away from Oracle, actually, to a system like this, and they've had better performance and better reliability. Riot Games uses this for League of Legends for all of their kind of chat data around if you're in the middle of playing a League of Legends game. The Basho React database uses CRDTs. We're seeing tremendous adoption by companies that are not deploying these things at small scale. OpenTable has their own version of CRDTs as well. I mean, it's been very successful. In terms of lineage, we've seen systems like Spark be able to have massive success over Hadoop because they have this recoverability property, which comes from this lineage property. And finally, Epidemic Broadcast has been incredibly successful in metadata management for large-scale databases like the database Cassandra and React. Both use it for metadata management. And so we've seen that these systems provide very high reliability, but are also very efficient. And so what I'm trying to say is that can we combine these 3 independently successful techniques to kind of rethink the reference architecture for distributed programming? And so I'd like to thank my colleagues all across Spain, Portugal, the UK, and Belgium, who have provided a tremendous amount of programming and research and proofs and all sorts of stuff like that. So thank you very much.
Hi, Samir Ajmani. I manage the Go programming language team. You hit on this towards the end, the expressiveness of the programs you can write here, and I'm just curious what sort of examples you've actually just tried to write to get a sense of that expressiveness. How far have you tried to push that with case studies?
We've only been kind of focusing around, so right now we're working on a large-scale evaluation in terms of seeing how far we can deploy the runtime. And so most of the focus has been on that just because we have a hard deadline at the end of the year for an EU report that we have to write. But in terms of the applications we've looked at writing this ad counter example. We've looked at writing averages, like doing rolling window averages across a large number of mobile devices. And so the average is problematic because either you end up tracking a lot of garbage or you end up losing kind of precision. And you kind of have to not model the division calculation. You have to model it as sums and counts. And
for what it's worth, when we monitor large-scale distributed systems, we typically don't want to do average calculations like averages at the endpoints. We typically just export the sum and the count, and we do things like average calculations at the sort of monitoring layer.
That's what we're doing as well. Yeah.
So that actually turns out to be best practice when we build production systems as well.
Okay, yeah. So yeah, we're modeling it the same way. The idea was, can you express it in a, so the idea was to kind of get the way you could write the program down to 1 or 2 lines of code for deploying the application. And so you can express this average with just a fold, with just a single fold line in like a higher level, in a higher order language. And so we thought that was a very interesting thing because you're not talking about distribution. You're not explicitly talking about where you're sending that information. We want to kind of automatically derive the distribution for it. And finally, we've looked at some examples around a virtual wallet use case that's come from Rovio Entertainment, which is about doing quantity transfers between like a wallet. So like I might have some coins and I buy a hat or something. And so some of these operations, we've looked at what it means for the language to have a notion of transaction or atomic visibility. And so we have some work that's not yet published, but it kind of tries to relate these two things. How do you think about transactions in a programming language when you don't want the user to actually explicitly write transactions?
Hey, Chris. Two things two things in particular stood out to me. Both you mentioned in the IoT space farming out, computation to the edge and so as to more appropriately handle computations and data, on the edges of the network. And also when you spoke about working with Lasp and working, on the joint semilattice, how that there was a subset of computations that you really couldn't do as a client and had to relegate to the server. I'm curious as to where you draw the line between code that can be, farmed out to an edge node or can be done in the semilattice, because these seem kind of spiritually similar. But as an industry practitioner, I'm not exactly sure what kind of work I can safely farm out to the lattice or farm out to the edge nodes. Is it just arithmetic computation? Is it, can I do some meaningful statistical work over here? Like what kind of landscape do you see in a world where we're effectively farming out our work both on the semi-lattice and onto edge computations?
Yep. Yeah. So I guess the high level answer to that question, and so we've done a bunch of thinking about this, but the high level answer to the question now is what we're trying to do is slowly introduce. So we're working on operational semantics for the language, and so we're trying to slowly only introduce things that would be able to be run on both. Run in like a data center client and be transparently distributed. We're trying to guarantee that you cannot actually express something that would produce a computation that's not correct by construction. And so there's a couple interesting things there. So there is prior work on kind of doing analysis if you look at the COM theorem and the work done by UC Berkeley on Bloom, where you might be able to say, well, if I introduce things that potentially are non-monotonic, then I can perform an analysis of the code to detect those points and introduce coordination. And so that's kind of a known quantity because that work's already been published. And so what we're trying to do is say, well, can we kind of push it as far as we can with building stuff that's only correct by construction that can be transparently distributed, and then when we get to examples like I mentioned earlier with transactions, we have to say, okay, well, how do I get atomic visibility? I actually can't do an exactly once quantity transfer and guarantee it's safe without massive amount of state and coordination to kind of do it correctly. And so we're trying to slowly introduce those things. And I guess the final point is, I guess the final point around that is, Yeah, I mean, there's a tremendous amount of work to be done around the semantics to prove that, like, arbitrary, when you start to deal with the optimized data structures that don't store as much garbage as the ones I showed here, making sure that those transformations of the lattices happen are really difficult to ensure correctness. And so trying to come up with a general proof theory for this is kind of important before we introduce anything else. And I guess one final point is that we acknowledge in the same way that the UC Berkeley group did with Blazes that at some point you're going to have to extract a value out of the system and do something with it. And so we provide kind of operations, so we think of it kind of monadically, right? And we provide an operation that's going to say, well, like, I am opting in to pull this out of the system, and I know that once I do, I lose guarantees. And so, you see this is a very similar idea that was in both LVARs and Bloom, Daedalus, and Blazes. So this is an idea that's been thought about a lot, but nothing amazing has really come other than you need to know that there's a punctuation point if you want some notion of safety.
So given the conditions for monotonicity means that you are excluding the possibility to model industrial processes or similar where you want to have a feedback loop.
So the way, so we do have this. This was briefly mentioned. I didn't explicitly mention it, but it was briefly shown in the ad counter example. Is that in this slide here, where we say that when an advertisement meets some criteria, like it's shown too many times, and we have to disable it. So you could realize this as a cycle in the graph. And so we actually can think of this operation as a delay that breaks the graph up into, that converts the graph from a cyclic graph to an acyclic graph with a delay. And so this operation here that thresholds and says, oh, I've displayed this too many times, will actually inject a new event into the system. And so from a semantics point of view, we can actually reason about this as a cyclic graph. We can determine when we have quiescence in the graph because we can look at the semantics and we know whether there's a pending operation that will be injected at a future time or not. And so this is how we kind of analyze it from a non-quiescent to quiescent. Yes. Yes, you're welcome. Good question, though. Yeah. Very recent stuff we've been thinking about.
You addressed some of this a little bit earlier, but can you talk a little bit more about how systems like this can be engineered to operate in environments where you have hard time bounds? Meaning, I have to get, when I get to time X, whatever information I have is what I'm going to have to make a decision on.
Yep.
Without understanding that the underlying infrastructure may not be able to deliver all of the information that's happened at some of the distributed nodes during that time.
Mm-hmm. I don't know if I can really say anything really amazing about that. I guess I guess the point is that from the point of view from the language engineering point of view or the model engineering point of view, we think about it as computations that will eventually be correct. It will eventually reflect the total state of the system. I don't really have any really great intuitions or insights on hard bounds, but I would intuit, I guess, that if you needed to enforce some sort of hard bound, what would be nice is to have a way to analyze the program and say, well, you need to get a value from point A to point B, and given the kind of data flow mechanism that you've built or given the topology you've outlined, kind of prove a negative result to say that given your application design, you cannot do this without coordination. And so I think there's probably an interesting bit that probably relates to the Bloom work, because they're able to do analysis and say, so they do it around retraction of information to say, if I want everybody to say, if everybody agrees Chris is on stage, and then I want everybody to agree Chris isn't on stage, the system is able to tell you, hey, that's something that needs coordination because you can't get that agreement other than that. You'll risk programming anomalies. And so maybe there's interesting work to say, given a particular topology and given the computation deployed across that topology, do I know that there are certain circumstances where a value will be delayed for a potential unbounded time because it crosses a node boundary? And so if you think of all node boundaries as as some node boundaries as weighted and some node boundaries as, unbounded delivery time on the message, then maybe you could provide a formal analysis to actually make those guarantees. That's actually a really interesting research project. So.
Thank you.
Okay. Well, thank you very much.
Thanks, Chris.
Thanks.
We have a very short break now before the next talk. The next talk is going to start up at 2:40, so approximately 10 minutes from now. So I'll see you back here then.